Hello, and welcome to the Engineering Dynamics Course Companion. Today is Class 11. We're continuing with the kinetics of particles, and today we're going to deal with direct impact on particles and the conservation of linear momentum. As always, you could go out to the description and click on one of the links to go to the latter part of the video and go right to the example. For the bottom line up front today, what we have when there's no external impulse, we have the conservation of linear momentum. So the sum of all the momentums in the beginning state is going to be equal to the sum of the momentums. Let me say that again. The sum of all the momentums in the initial state is going to be equal to the sum of all the momentums at the second state. That is the conservation of linear momentum. And want to recall, though, as we're doing this, that these are vectors, right? So they have vector hats on top of them. When we have the case when we have the collision and impacts of particles, we have something called the coefficient of restitution that's necessary to try to figure out what the final velocities are of this collision between things. In the class today, we're going to deal with direct collisions. In the next class, class 12, we're going to deal with oblique collisions. But the thing that we need to use to be able to find what's going to happen in conjunction with the conservation of momentum is this thing called the coefficient of restitution, which we'll talk about some more. It's the ratio of relative velocities after and the negative relative velocity before, right? So taking a look at this E right here, we'll look at that a little bit more closely, but it'll help you to remember what that equation is. Conceptually, the coefficient of restitution, it can be thought of as sort of, but not quite, an efficiency of the impact, right? When something is perfectly plastic, it means that when the two things hit each other, they stick to each other, and therefore the coefficient of restitution is equal to 0, right? If something is perfectly elastic, right, it's going to perfect bounce off of the thing, and the collision is going to have a coefficient of restitution equal to 1, right? And it's similar to efficiency of collisions, but it's not quite the same. But there is something that we should consider, that we can use the coefficient, like linear momentum can be conserved where energy is not conserved, all right? So because if there's the coefficient of restitution is less than 1, that means it's not a completely efficient collision, and there will be energy lost during that. So we couldn't use the conservation of energy as part of that, but we can use the conservation of momentum. It's an interesting thing. All right, so impulse and momentum can have multiple particles going on, well, most of the time when this happens. Like pool is a very common example we might think of. I do a example in the next class where we have pool balls hitting each other. So we start out with that impulse and momentum. And if there is no impulse going on right there, we just have the momentum, total momentum, before equals the total momentum after, right? So what's taking place? How can we get rid of an impulse? We know there is some impulse. Well, what happens if we have multiple particles? The impulse is going to be, when we take both particles together in our impulse and momentum diagram right here, what happens when they collide right here, when there's a collision, there's an impulse on that one, force times time, but is equal and opposite to that one. So they cancel each other out. That's if you have both particles included in the impulse and momentum diagram, right? That's an important thing. So what is really taking place here, right, is we have impulse and momentum before and impulse and momentum after right here. I'm not sure why I have this second diagram down below. I guess, okay, so right down here in this one right here, we have this thing taking place, and now there's a difference. Like you'll notice the magnitudes right here. This is large and that's small. Of course, therefore it catches up. There's an impulse that takes place, and now this one is large and that one's small. But here is this scenario where they stick together right here. So now they're stuck together. So that might happen. That would be a coefficient of restitution of 0. So what takes place is now they're traveling and this one catches up and now they're stuck together and now there's a new momentum of them moving. So and so that can be done. This can be done when it's perfectly. This can be done without the coefficient of restitution. But now, a lot of times we'll see when we set up that problem, there's going to be two unknowns, and quite often they're going to be the final velocities. There's one equation and two unknowns. So we need a separate equation. And what that is the coefficient of restitution. I abbreviate that as COR. And this is, you'll notice, this is the relative velocity after, right? So B minus A divided by the negative, easy to forget that, relative velocity after. So you notice that's A minus B. And this is 2 on the top and 1 on the bottom. So a little bit easier to remember. And so perfectly, so looking at this equation here, let's check out when we already mentioned that the coefficient of restitution when it's perfectly plastic is equal to 0. Well, that means that this guy has to be equal to 0, right? So the relative velocity afterwards is equal to 0 because they have the same velocity, right? If it's perfectly plastic, that means they're sticking together. If it's perfectly elastic, the relative velocity before is going to equal the relative velocity afterwards, except that they're going to be negative, right? So the relative velocity has reversed between the two things, right? So what's taking place in this collision as the coefficient of restitution, right? So here is, by the way, here's the two equations that we will need to solve things, right? We have this conservation of momentum is the first equation, and the second equation is the coefficient of restitution. So quite often, this is an unknown and this is an unknown. And so we can't solve it without having this extra equations. This is an unknown, and that's an unknown, the velocities afterwards. So what happens during this collision is the particles will first, they'll touch each other, right? And the collision starts. And then they start to deform. They start to squish, right? So you can almost picture them getting getting smushed up to each other, and this is happening very, very quickly, and it's a very, so we'd have to have like a really high-speed camera to be able to see that. Now they deform, and then at some point they stop deforming. And what happens now is there's some strain energy. You could think of like a spring being compressed, right? And that spring energy is stored, right? But now they start to decompress. They start to rebound. They start to bomb. They start to pull away from each other as that spring energy that was stored starts to release and push each other away, right? And now they begin to become disengaged, right? They become separated. Okay, so what happens when there's a coefficient of restitution that's between 0 and 1 is that there's not a completely this part right here doesn't completely give back all of the energy. It could be through increases in heat, probably not enough that you could actually measure it, but it is. It could be sound, that sound vibration that gets dispelled, right? And also just because of the nature of the world, there's often just a certain amount of entropy. Okay, so here's the example. We have two balls. Now we have to kind of imagine that these balls are going to hit each other in the center, even though one is smaller than the other. But we're going to these are particles, so we're going to ignore the physical size. But the size here is just to indicate that one has a larger mass than the other. So we have ball A is traveling is 2 kilograms, and it's moving at 6 meters per second to the right. And ball B is 6 kilograms, and it's moving to the left at 4 meters per second, right? And they're in the opposite direction. We want to determine the velocity of the balls and the efficiency if the coefficient of restitution varies between 0 and 1 in increments of 0.25. And we want to graph the results of the efficiency versus the coefficient of restitution. So we might have a problem where we were given the coefficient of restitution 0.8 is a very popular one that lots of problems usually like to have. And then we might want to find the velocities. But here I've made it a little bit more complicated where I said, well, let's just check out what it's going to be, that coefficient of restitution, and then graph and kind of see what it's like compared to the efficiency, because I said they were like efficiencies. So here is the initial momentum diagram right here. You'll notice that I've moved the ball so that they're going to hit each other right there on the center. I've defined what my coordinate axis is going to be, and now I define, here's my impulse taking place right here. I draw those in there, and then here is the final state. And I don't actually know which direction is going to be the final state, right? Because it could be that ball B is has so much more momentum than ball A that it sends it going in the opposite direction. And since I don't know what that direction is, what direction the final direction is going to be, I'm going to choose it to be in the positive direction and see what the result is going to be. So we assume the positive direction. So we write out the conservation of momentum here. And we see when we plug the numbers in that VA2 and VB2 are unknowns, right? So that's equation 1. We have one equation but 2 unknowns. So now we take the coefficient of restitution and we write in what these are, and then we put in these initial velocities, and we set that equal to equation 2. Now I've set E as a variable so that I can now start entering in things right here. So here I've made it into equations, these 2 equations right here. And what I can do is, if I have a table of my E ranging from 0 to 1 in increments of 0.25, I can find what my velocities are going to be, right? So what's interesting here is what my results will be for each of these E's. I get negative for both VA and VB. That means they're both traveling to the left. But now, when we have the coefficient of restitution of 0.75, we note that now VB actually, ball B actually starts going into the positive direction, right? So it actually bounces back some, right? So let's see, and we can also figure out when will the ball stop, right? When is it going to stop? Well, that's when we find it. We figure out that that's actually going to be 0.6. We find that by setting this equal to setting the velocity of B equal to 0. Interesting things, and in fact, we could actually, that could be like the way that the problem was stated, and it would be an interesting variation on this problem. We also want to figure out what the efficiency is. So the efficiency is going to be the ratio of the kinetic energy at the end to the ratio to the kinetic energy when it starts, right? So here we go. We got energy before is going to be the kinetic energy of both of the balls, and then the kinetic energy at the end is going to be the kinetic energy after. And note that they're both still variables in here because we want to find for this range of things. So if you use the results from that previous table right here, we end up finding right here. So the kinetic energy is the same for all of these, right? Because it's the start. But we can see what the kinetic energy is for E afterwards, right? So here is for perfectly plastic, we can see that it has a 10% efficiency, right? But when it's perfectly elastic, we could see that it has 100% efficiency. That's an interesting. Something also of note is that the velocities are squared here, so it didn't matter whether they were negative or positive, reinforcing the idea that impulse and momentum is a vector, whereas work energy is a scalar. I want to remember that. And here is a plot of those efficiencies. Now, something of note, all right, so I said the coefficient of restitution is like an efficiency, but it's not equal to efficiency, right? Obviously, 0 does not equal 10.7, and you could see this trend right here, and it's not a straight line. It does have a curve, and this is, by the way, not this will differ for depending on the situation, right? It'll depend on the masses of the balls, and could depend on the velocity of the balls as well. So this efficiency is not always correlated to that coefficient of restitution, but there is some type of relationship going on here for this particular scenario. So that's the example for this one. We'll have other examples for oblique in the next class. For more examples of for this chapter, and there's probably 3 more. There's usually about 4 examples in every book. Let's see. Let's check out chapter 11 and. Let's see. Oh, that's the wrong one. Oh, it's the right one. Is it the right one? Yeah, it's the right one. Okay. Yeah. Well, don't fold the pages. This is nice. This is the hardcover edition of this. Let's see. That's chapter 12. Let's see. How many examples do I have? Let's see. Yeah, this was example 11.2, I think, in the book. Yep. And then we have 11.3. Sure enough. Oh, and then we have 11.4. Yep. So there's 4 examples in this chapter. Chapter 12 is the next one. That's oblique impact right there. So these are the hardcover editions. We also have I like hardcover books, but there was a soft cover edition, and there's also an ebook that you can also acquire. These are the books right here. They're published by Morgan and Claypool. Look down below into the description to find links to acquire the books. They're also available on Amazon. And please subscribe to this channel. And feel free to add comments, questions. Can't say that I'll answer your question, and if I do answer it, it might not be really quickly, but I will read them. So until next time.